So good morning. Welcome to Krishna's classroom. Let us continue with our discussion on some more examples before we take up the concept of orthogonality. Now we take up the following. I believe this is the number or 4 or something like that. Yeah. Let it could be as well depending on what field you are using. Be the n cross 1 column matrices with entries from C or R, depending on whether you are working in C n cross 1 or R n cross 1. Let invertible matrix with entries from C or R. So this bracket means that you read the statement with Cn plus 1, then you use C here. If you are reading with Rn cross 1, that means on the real space, then you would have to use the bases. It is not CR, it is actually C or R. Okay, so don't get confused with it. Now define for inner product of x with y as x star q star q now what you have is this x star is transpose q. So what one has is this. See, x is given by then And so also Q star for Q star conjugate. That means you are taking, see, Q star, suppose we denote this by Q J K star, then it's a transpose conjugate that you have taken. Then you see that, see, we have 4 terms here. This is a 1 by n matrix. This is an n by n. This is an n by n. And this is a n by n. So you end up with say 1 by n and n by 1. So this is a 1 by 1 matrix. That means it's a scalar. Okay. Now one verifies that all the properties of the inner product are satisfied. That is just routine work. So this is essentially, what you have is this. This is essentially Qx, Qy. So this is actually equal to Qx dot Qy. This is a standard inner product, so let me just mark this with standard inner product. Okay. Or I can just put here S. I'll put some S and then define sigma so that is what you have. So you get, so see what is significant is that Q is an invertible n by n matrix. So for every invertible n by n matrix, you have a inner product defined. Okay, in this way, right? Now, more specifically, see, you see that it's star and this is equal to and you see that since Q is invertible, you see that Qx equal to 0, note x equal to 0. So we make use of that. Therefore, this is equal to 0, which in turn means x equal to 0. Okay. That is, norm x equal to 0 means norm of Qx, the standard inner product, equal to 0, and since Q is invertible, you get, this implies Qx equal to 0. That is possible when x is equal to 0. So that proves it. Now we give a more general version of it. So that means what is the implication? The implication is that if you have an invertible matrix Q, then using that one can always define a inner product on Cn cross 1. That means different Q's will define different inner products, of course barring some kind of relationship between. So you can investigate what happens if Q and Q1 and Q2 are similar, what happens to the inner product. So these kind of questions you can ask. Right. Now we look at the following problem. Okay. Take another example. This is in a way generalizing this. Suppose C or R, depending on it's a complex space or a real space. Let with an inner product defined by that is, this sub W indicates that this is the inner product that we are looking at. Now what we want to look at is, so let T be a, that means a linear transformation from B to W non-singular. That is Tx equal to 0. That means the kernel of the map T consists of only the 0 vector. So various ways in which we can define it. Now define PT of inner product of okay, so this is the definition. So we claim that then sorry, not this. Yeah, okay, right. I'm sorry. Then PT is an inner product on it's quite easy to prove because if you look at, you can easily see that it is symmetric. I mean, conjugate symmetric if you are working on C. Okay, because what is the okay? So show that, verify. Okay. Denotes you want, you can put T also. V on V induced by T. Then you can prove the following, that is okay. This is equal to conjugate. That is quite easy to prove because you use the fact that this is an inner product. Convert this into that. So this is symmetric. That's the first thing. Second thing is that alpha u plus beta times that is linearity in the first variable which in turn together with 1 implies it is conjugate linear in the second variable. Okay, so you have the corresponding 2 prime, and then you can verify this. Greater than or equal to 0 and it is equal to 0 if and only if u equal to 0. So these properties one can easily verify and show that it's an inner product. Once again, this is a generalization of what we looked at in the previous example. Here what you have is that for any non-singular t, any non-singular t, once you have on the range space an inner product, you can induce an inner product on your original space. Now this is particularly useful because this is what we have seen in one of the earlier examples where, see, we talked about an ordered basis for a finite dimensional vector space, and then we looked at the representation of each vector in terms of these basis vectors, which in turn gives an isomorphism to Rn or Cn depending on what field you use. And then of course you already have your standard inner product on Rn or Cn that induces a inner product on the original space. So depending on the isomorphism that we induce, we can get different inner products. Now you just recall. So let us make a reference to it. That's in fact a special case of this. So recall the example. Namely, definition of V. Okay. Now how did we do that? We had chosen an ordered basis this induces a natural isomorphism of defined by psi n Now this is well defined. So phi is the isomorphism. Okay. Now we use the standard inner product. Inner product where eta n. Now define UV on V defined by sigma where psi is equal to okay. So this is essentially the same thing that you have here with T appropriately chosen. Now for W we are choosing Cn or Rn, and then phi we defines the linear transformation from V to Cn. So this is just that. Okay, so this is a special case of that. So this contains the possibility of introducing several inner products on the same space. Now we different inner products endows the space with a different geometry, a different concept of length and a different concept of angle. But essentially or abstractly, they endow the space with a concept of length and angle. Now this is what we are going to make use of. In depth, we will take advantage of the so-called inner product and our experiences on working with Rn or on R2 or R3. We will try to generalize whatever we can generalize in the more general scenario. Now we are in a position to introduce the concept of orthogonality. Let us recall the following. On R3, computed angle between two vectors in terms of coordinates of the two vectors. Cosine of the angle, let me write. So cosine of the angle that we have computed. What was it? Suppose x equal to e and xy belonging to R3 the angle between basis, that is the standard basis are, that is we have okay. Then what do you have? Then we have seen that cos theta equal to half this is what we have seen. Then we observed that this is equal to so in short what it says is that where theta is the angle between so let me make it clear in a diagram. These are the this is a standard basis, and then you have two vectors. This is y, so this point and this is the angle between them, so denoted by theta. And cos theta is given by x dot y, or what you call x inner product y, same as x dot y, divided by norm x into norm y. Okay. Therefore, see, we shall, okay, we observe that equal to zero if and only if equal to 0. That is, if and only if equal to 0. This is an observation that we make that works in R3. The same case in R2. R2 you will have only two components and you can easily work this out, or we have already done it. If we have not done it, we can easily work it out. These are the coordinate axes, or the unit vectors in these directions. In terms of that, you are writing this psi 1, psi 2, psi 3. Okay. So essentially, if you want, you can see this. So this distance is psi 1. this height. Psi 1, psi 2, psi 3. These distances are denoted by psi 1, psi 2, psi 3. This is the usual Cartesian coordinates. Now that prompts us to define. Okay. So if, okay, let us write this. With inner product of uv introduced in some way. That means a function from v cross v to C or R with the properties of symmetry, linearity in the first variable, conjugate linearity in the second variable, and positive definiteness. Okay. So if such a function is there, then you can easily work on that. So that's our next. So how do we define this? So we have the concept of orthogonality in R2 and R3, the usual concept of R2 of orthogonality on R2 and R3. We are trying to discover that. So we take V an inner product space over C or R with then define orthogonality as follows. We say that U is orthogonal to if and only if inner product of equal to 0. That's the definition. U is orthogonal to V if and only if inner product of U with V equal to 0. This is the natural generalization of what we have observed in R3 or R2. Okay. Now I want to make a remark here for the sake of students. You see that we have lot of experience of working on R2 and R3. The geometry is visible. You can draw pictures. You can get a feeling in 3 dimensions. Use it in very many areas. Now we are trying to induce such concepts into the general scenarios. So we are trying to make an inner product space a natural generalization of R2 or R3. Okay. So we have taken up the concept of orthogonality there, and we represented the cos theta, where theta is the angle between two vectors in R2 or R3, in terms of the inner product or the dot product. Okay. Now, taking a clue from there, we now define what is called orthogonality. So you say that U is orthogonal to V if and only if this is the definition. And this checks with whatever experience we have over there. Okay. Now you immediately see that, see, if you look at C2 or C3 or even C over C, is not something where you can conceive in terms of pictures. Okay, so we make some remark about this. Note that this is a concept symmetric. Why it is so? You see that is V is orthogonal, or U is orthogonal to V if and only if V is orthogonal to . This is because, you see, UV equal to 0 implies equal to 0 . Vishal. By the notation U is perpendicular to, okay, so this is the notation. Now we make certain observations. 0 is orthogonal to every element of that is, I mean 0 belonging to V, orthogonal to every element of V. That's quite easy. That is because this is because the inner product of 0 with V equal to 0. So if UV equal to 0, either u is 0 or v is 0. It comes from that. Now you see that u and v, the inner product of u with v may be 0 even otherwise, even when u and v are not 0. We can now talk about the set of all vectors orthogonal to a given vector. Okay, it becomes interesting when the subset consists of non-zero vectors. That is 0 is perpendicular to okay. S be a subset of okay. S non-empty. I am not attributing any structure, a specific structure, except that it's a subset of V, but otherwise no other structures, no assumptions are made. Now we can define what is called S per. S per is the set of all vectors V belonging to V such that the inner product of V u equal to 0 we denote this way, we call this S per. Make some observations. If consists of only the 0 vector, then S per. If zero. So you cannot say that S per equal to 0 means S is equal to V. Need not imply S is equal to. For example, let V be equal to R3. Where Ej equal to so that these three vectors Okay. Now you observe that S per 0. Now that you verify. Okay. So this statement is substantiated by this particular example. So we make another observation. S per is a S per is a subspace of V. Okay. That is quite easy to prove, so give a proof. For example, in R3, see, every time you see a new result, you just see what it means in R2 or R3. So in R3, suppose you take S equal to, say, simply E1. What is the, so that means, okay, so, or more generally, suppose you take R3, you are given a vector, say, now what are the vectors which are orthogonal to this? That is all eta such that eta dot psi equal to 0, which essentially means a plane passing through the origin eta with the property that the angle between psi and eta is equal to 0. So that gives a plane. So S per, in this case, is for psi not equal to 0. Therefore, in this case, we are taking S to be equal to the singleton vector psi. So S per is then a plane passing through the origin. So S per a subspace of V is in fact a proper subspace. In fact, if psi is equal to 0, then you have seen that it's the whole of V. Okay, so that's a special case of that. But this is a non-trivial subspace, and you see that this is whenever psi is not equal to 0, the corresponding S per is a two-dimensional subspace of V. So we have got similar concept in the general scenario that we will examine. Okay, so you have now the concept of S per. Now you see that suppose S is a proper subset, or or S is a subset of Then we have S perp. S perp is a subspace of V, which you can give a proof for that. So prove that S perp is a subspace of. That's easy to prove. Now look at S perp. Double perp. That means the perp of S perp. Now you see that S perp now note that therefore S is contained in, that is S is contained in. Now you ask the natural question, suppose this is a consequence of symmetry. Symmetry of that relation of orthogonality. Suppose S is a subspace of V, then here we assume otherwise there are some difficulties. Okay. Now these are the straightforward consequences of the orthogonality, the concept of orthogonality. Now we introduce some consequences of this in our next lecture. So we continue with orthogonality and its consequences, and then prove results like the Bessel's inequality, etc., etc., and Parseval relationship. Many things that you have direct experience on R3 will try to prove here. Okay, so R3, I said R3 is the model. Okay? So a lot of things you can expect to be true in general. Okay, so it's a very worthwhile generalization of the concept of dot product to the so-called inner product. Thank you very much.